Good afternoon, students. Am I audible clearly? Good afternoon, students. Am I audible? Okay, let us start with the fourth chapter in the syllabus. So before starting with the fourth chapter, in the third chapter, we have studied about SQL language. Complete SQL language we have seen into the third chapter, where we have seen data definition languages, data manipulation languages, authorization languages, and few commands for the transaction system also. Now we are moving towards the fourth chapter, that is relational database design. So this is considered to be the last chapter in the first section, relational database design, where the main focus is given on the normalization. So let us see which are the syllabus points. So these are the total syllabus points. Total 6 points are there. So syllabus contents are features of good relational design, atomic domains, first normal form, decomposition using functional dependencies, functional dependency theory, algorithms for decomposition, and the last point, decomposition using multi-valued dependencies. So these are the points which we are going to study in the first this chapter. So previously also we have seen many schemas, relational schemas regarding instructor, department, etc. So we are having the schema for the instructor or department relation is, still people are joining. So for the department relation, we are considering the schema as department name and then building in which it is situated and budget. So this is the general schema which up to now we are using for the department relation, and for the instructor relation we are using the schema ID of the instructor, name of the instructor, department name of the instructor, and salary of the instructor. So these are the four attributes which are we are considering in case of instructor. So now here, whatever department name is there, this is getting repeated in department relation as well as in instructor relation. What if we decide to combine the schema of these two relations? Any idea that we can combine these two relations? So in order to combine, let us take that I'm having an instructor from the history department, that is instructor 1. Let us consider ID with name A, B, C, and department name as history, and salary consider 78K. Okay, so this is the uh, any tuple from the history. I may be having value set like history. History department is located in consider Watson building, and budget of this department is considered 45 lakhs. Okay, so during this period, so now if consider we try to combine these two schema together, how we can? So in order to combine these two schemas, here the common attribute between these two is a department name. It means that if I wanted to have a common schema, so I cannot make department name as a primary key here. Even though this is a primary key into the department relation, I cannot make this as a primary key in the instructor relation, because in the instructor there may be multiple instructors belonging to a single department. Okay, and that's why we cannot make department name as a primary key into the combined schema. So here I can go with the structure ID of the instructor, name of the instructor. Let us take salary first, or let us take department here only. Department name, then salary, and with respect to the each department I will mark its building, and its budget too. Okay, so this will be the combined schema for the existing relation. So because of this, whenever I am willing to enlist department, all the instructors from so and so building, maybe they belong to any department, then from a single relation I can get this data. But here the problem is that if consider there are four instructors available into the history department. Okay, consider ID 1, 2, 3, 4. These are the four instructors which belong to the history department. For the history, with each tuple, with each of these four instructor, we need to repeat this information also. Okay, that is, I will repeat one in between all the values. That is ABC department name history. Here also I will mark this as history. Okay, and then after the history salary, and then after the salary here I will repeat this belongs to Watson building and budget is the 45 lakhs. Okay, again there will be instructor 2 which belongs to, which may be having details anything which belongs to history department, and then salary may be something, and after that the history department is located into the Watson building, so this information will also get repeated here. It means whatever this part of the information is there, this will be get go on repeating so many times, as many times the instructors are there for first, second, or if there, even though there are 7 to 8 instructors are there, still this information will go on repeating. So this is the problem with the combined schema. So here we try to give the schema in such a way that minimum part of the information should get repeated. So here, in order to avoid this repetition, we are having this relational database design as a main chapter into the first section. So let us see, move towards the more details. So whether the main idea is clear, why we are moving towards the combining schema. So let us see. So this is the combined schema. So here we are combining two relations, instructor and department. These two relations, if we are combining, so here right now we are not focusing on the any relationship. Right now we are simply, it means what are each department, what are the relationship previously we have seen. Right now there is no connection with this. Right now this is a independent discussion is there. So here I'm having ID of the instructor, name of the instructor, salary, and whatever this department name, building and budget is there, this is my combined schema. So here Einstein, let us take a physics department. Okay, so Einstein belongs to physics department. So physics department is located into Watson building with budget of 70,000. Here, this part, Watson and 70,000. This is being repeated here. And this is being repeated here also for the instructor goal. If I take finance department, okay, in the finance department, I'm having instructor Wu and also I'm having instructor Singh. So here, for the finance, the department is located into Painter building with 1,20,000 as budget, and here also that for the finance, here also the same information is getting repeated. It means that if we combine the two schemas, department and instructor, some part of the information is getting repeated. Okay, so this will be the result of combining the two schemas, and hence combination of these combining these two schemas is not preferable. Right now, I may be having data of 12 to 13 instructor. That's why this won't take much more space. But if we take students' data or if we take any other detailed data, course-wise, etc., so this is going to take lot much space as there are thousands of students might be there, or 50 to 100 courses are also there. That's why this information will get repeated unnecessarily. So let us move towards the detailed discussion. A combined schema without repetition. So this is also one of the possible solutions. So here combining the schema always doesn't result into repetition of the information. Here this is the example which shows we can combine the result, we can combine the schemas without having the repetition also. So here we are having section class, one of the relations with attributes section ID, building and room number. And we are having another relation section with attributes as course ID, section ID, semester and year. Okay, so this is the so if we combine these two into single relation, so this will be having structure like this. But here the problem is that every course whatever we are taking, that information, that building and room number will not get repeated, because here section id refers to a simply either of the course of each semester or each year. That's why even though there is less possibility of repeating this section id, yes, there is a possibility of repeating the course ID, but whatever section ID is there, there are very less chances of repeating this, and hence whatever this combined schema is there, that will not have any repeated information, because in each year, right now we are dealing with the database course. So database engineering, this is the course ID which will get repeated each year. But right now, consider that right now whatever database engineering for the academic year 2020-21 is there, semester 1 is there. For this purpose I will be having any course id, and as this is a different section, let us take that right now section a 1 2 3 4 any numeric is there, which is conducted into some another building and room number mf504 or any other. So it means that for this particular semester, I will be conducting database engineering classes into this building, this room number. So next time, it means in the next year or in the previous year, it is not mandatory that I will be taking classes into the same division, same building, same room number. So here section ID is referring to that uniqueness, and hence this will be information getting different each time, and that's why whatever this complete section is there, this will not have a repetition of the values for building and room numbers. So even though this is repeating, section ID will be always a different one, and that's why we can combine the schemas in order to not to have a complex structure. So in this case, we may prefer combining the schemas together. So do you? So whenever we are dealing with the schemas, so now shall we prefer smaller schemas or shall we prefer longer schemas? So here, whenever we are talking about the schemas, actually talks about a functional dependency. Functional dependency. So this terms initially feels very difficult, but this term is very important in case of this fourth chapter, that is normalization. So here, before moving to this actual question, let us focus on few of the things. So suppose we had started with inst department relationship. Okay, this is the relationship between instructor and department. So if we try to decompose this relation, okay, how would we how would we know to split up decompose into instructor and department? Okay, so right now we are having the department schema as department name, building and budget, and in the instructor we are having schema with id name, department name and salary. So because of this we are having, so here we may make rule that each department entry should be once in the department relation, because we cannot repeat the department name, and hence department name we will consider as a candidate key. So here functional dependency, it means that denoted this is denoted by an arrow. So here denote as a functional dependency. Department name, on this attribute we are having two attributes dependent, building and budget. So here I may say that building and budget, these are functionally dependent on the department name. Okay, so here let us see the meaning in much more detail. So right now here let me come to the first page, okay, where we started. So now, or let us take an example from the second. Okay, right now I'm focusing about this uh, image only. So here I will crop this. Okay, right now here. So right now here, there are three attributes are there: department name, building, and budget. Okay, so now, do you think that building and budget will change whenever there will be a change in department name? So here, let us come through the tally. Physics, here I am having value for the building as Watson. So wherever I am having physics as a value, for the physics I am having building name as Watson only. And this means that whatever this existence of the value is there, Watson, so this implies that whatever this building name attribute is there, this is dependent on the name of department. So it means if my department get name changed, similarly building name will also get changed. Now here, if I'm having department name as physics, everywhere wherever this physics will be the department name, the same name, even though there are multiple tuples are there, consider T1 tuple and T2 tuple. Okay, if for the T1 I'm having department name as physics and building name as Watson, for the T2 also, if I'm having department name as physics, it will also have building as a Watson only. So let us talk in terms of alpha and beta. Okay, so I will use A and B attribute for this. If consider the functional dependency says that T1 dot A is equal to T2 dot A, then functional dependency it means that T2 dot B, that is another attribute, will be also equal to T2 dot, sorry, T1 dot B and T2 dot B. So this is the implication of functional dependency. Now let us take another example. So here, Watson, in the Watson building, I cannot, it means Watson, in the Watson building, I'm having physics department. Let us take a reverse case. Now another name, another, here I can find the Watson. So for the Watson department name, biology is there. So do you think that if on the building name, if I guess the building name, I can be sure that here department name will be fixed via this. Okay, can I guess or can I clearly say what is the department name? No. Here, for the Watson, one entry having it as physics, one entry having as a biology. It means that from the building name, I cannot compute or I cannot guarantee, I cannot give the guarantee about the department name. But if I'm passing the department name, okay, so then fix, I can give a single value for the building. There cannot be multiple values for the building. Okay, and so there will be a single value for the budget will be there. Physics, for the physics department, here I'm having 70,000 and here I'm having 80,000. Such case will not be there. If here is 70,000, if here is 70,000, in the next tuple also the value will be 70,000 only. So this is the case of functional dependency. Now let us take an example of the history department. For the history, I'm having painter as a building name. Here also, I'm having painter as a building name, and this 50,000 value and 50,000 value. These two values are also getting repeated. It means that budget and building. This both values are dependent on the department name. Okay, so clear with this functional dependency? Clear with this functional dependency? I'm not getting whether you are clear or not.
Ma'am, can you explain once again?
Yes, I will. Uh, Let me take some another example for this. Okay. So consider that I'm holding student name. Okay. Forget about the current schema. I'm taking the new schema. I'm having the current student name and addresses or city of the each student. Okay. So consider that the student has applied for the mini sports exam. Sport. No. Okay. Right now, this is my example. Okay. Now, here I'm storing the information like here I will store information. Okay, consider I'm having A students which is living in the Pandharpur. Okay, I'm having B students who is also living into Pandharpur. Okay, and another student C is there who lives at Solapur. Okay, now here uh, let us take this as a first name of the student. Uh, and I am also having these students who is living into consider Pune. Okay, so now based on the name of the student, can we guess in which city the student is living? Okay, so this is belonging to the address part of the student. So now do you think that for A, I'm having only single value here. Right now consider I given the restriction that student can give only single address or permanent address, etc. So in that case, for A, if I'm referring to the city, there will be only a single value, Pandharpur will be there. So now it means that from the name of the student, I can guess fit in which city the student is living. But now, if I take now the question comes. Now the question comes by knowing the city. Okay, so by having the city value, can you guess the name of the student? Can you? Well, this will give a single value. If I'm having the Pandharpur name as a city name, okay. So now, can I get a single value here? Here I cannot get a single value because A and B. It means there are two. There might be multiple students who are belonging to the But by knowing the name, I can give a single value for the city name. This means on city name is dependent on the name of the student. Okay. Similarly, here I will insert one more. Let us take marks of the students. Okay, consider this student is having 70, another student is having 77, another student is also having 71, and one more student is having 70 marks. So okay, so here now the value of 70 marks is dependent on the A. It means for A, if I'm calculating the marks, or if from the name I asked what are the marks of the A, then I will get a single value, that is a 70 value. But if I ask the reverse question, by whom the 70 marks are scored, then there are multiple values like A and D will be there. It means by knowing only the marks of the students, I cannot check about whom the user or current user is asking me, whether the asking student is A or whether D, where marks are insufficient to give me a single name here. Okay, marks cannot give me a single name, but name can give me a single value for address also or city also, and name can also give me single value for the marks also. It means here marks are dependent on the name, and city is also dependent on the name of the student. Now is it clear? Now is it clear? So this is called as a functional dependency. So combined schemas where information is getting repeated, where it is not getting repeated. So we were talking about the smaller schemas. So smaller schemas, let us first read this explanation. So if we write a rule, if there were a schema, department name, building and budget, then department name would be a candidate key. Yes, definitely it will be a candidate key, because for single department, I'm having single value for the building. This will be definitely a candidate key will be there. And so this is the how the functional dependency is shown. So arrow from the attribute on which the remaining attributes are dependent. So arrow goes from the main depart main attribute to the those attributes which were dependent on that attribute. So in the inst department and budget of department may have to be repeated. It's okay. This indicates the need to decompose the inst department. So here, what are our previous schema was there? There we were repeating the same tuples, and that's why we are decomposing this schema. So not all decompositions are good. Suppose we decompose this employee ID, name, street, city, and salary into, if we divide this into employee one, that is ID and name, and another relation employee two with name street, city, and salary. So here, let us see how this can be harmful. So this, whenever there is a if we are unable to take the same relation as the previous one, so this decomposition is always called as a lossy decomposition. So this one is the example. So right now here, consider that the previous schema, the employee schema, ID, name, street, city, and salary is there. So this is the ID primary key, and that's why this will not have a repetition of the value, but name is getting repeated, and even though name is getting repeated, this the two persons are different, and that's why street, city, and salary are also different. Relations, ID and name, and remaining attributes as name, street, city, and salary. So in this case, if we perform the natural join of these two relations, okay, natural join, it means that whatever the common attributes are there it will check for the equivalence of the values, and hence here whenever we are trying to perform natural join of these two, so this first relation, let us consider this as employee 1 and this as employee 2. Employee 1 dot name will be equal to employee 2 dot name, and if both are equal, we will go for the adding it to the output part. So here the first tuple, let forget about the remaining 57766 came. This will be compared with the first came, name got equivalence, and hence the first tuple will be 57766 came main, very rich, and 75,000 salary. So this was the first. Uh, it means this tuple was available in the previous relation also, and we recovered the first tuple. Next, whenever this comparison is done, along with side as name is also getting equivalence with the second name in the list, and that's why we will add another one more tuple to the output as 5766 king. This king will get equivalence to the second king, and hence street Northampton 67,000. So this record will be also become the part of output. Similarly, for the second entry, comparison of second tuple from here with the first one, equivalence of the value, and this one with the equivalence of the values, and hence because of this, even though in the main relation we are having only two tuples with name Kim as these values, in the output we got four tuples with because of natural join, and this is said as a loss of join because we are unable to find out which were the original tuples were there, and hence if we getting an extra information or false information or incomplete information, this type of the join conditions or this type of the recovery is called as a uh, lossy join, where we are trying to get the information which is a false information. So clear with my explanation, or is it getting too much difficult? So okay, please go through this example for a minute and let me have the queries. Clear with this example? May I move further? May I move further? So here, whenever we are getting, so this one is the example for the lossless joint decomposition, where we divide the relation or decompose the relation, but at the end we will get the same relation as the previous one. So in this case, here I'm having the main relation as R with attributes A, B, C. Here, if I divide this relation into R1 and R2, R1 with the attributes A, comma B, and R2 with the attributes B, comma C. In this case, we will divide this relation. Consider there are two tuples. So these two will be the part of this first relation R1, and second, these two will be the part of my second relation. And if we compare or if we perform the natural join of these two, then we will get, that is alpha 1 and 1a equivalence value, beta 2 and 2b equivalence value, and there is no other possibility of joint condition. That's why at the end we are able to retrieve the same relation as the given relation. So this R and this R both are same. So in this case, we can say that the decomposition of R into R1 and R2 is lossless decomposition, and whatever the joint condition we get or joint output we get, this is also same as R1. So this will be called as lossless joint decomposition. Please go through this example.
Slide. Slide visible.
Yeah, ma'am, it's visible.
नहीं ये तो जाते हैं. Okay. I wanted to see who are the people online for a minute. Okay. Position. So which actually able to recover the original relation after the joint condition. So while dividing the relation or decomposing the relation, we must consider how we are decomposing this relation. So let us move towards the first normal form now. So already we studied about the atomic domains. So atomic domain, it means that the domain which cannot be divided further. Just like phone number we have seen in the mobile number, we cannot divide the 10 digits apart, that this is subpart, this is subpart, but we can divide the name, that is first name, middle name and last name. So in that case, name will be called as a non-atomic domain, and mobile number I can say that this is a atomic domain which cannot be divided further. So here we are talking about the first normal form. The first normal form says that whatever the domains or whatever the attributes we are having into the relation, all must have the atomic domains. So okay, so let us read this once. Domain is atomic if its elements are considered to be indivisible units. Okay, indivisible units are there. It means that we can say that the domain is atomic. So examples of non-atomic domains are set of names, composite attribute just like address, etc., and identification numbers like CS101. We know the course names, course IDs are there. That is, if for the computer science I'm having, so CS, these two digits will give us the branch code, and next it will give whether first year, second year or third year, and this remaining two digits will give us the subject code. Okay, sorry, this one is regarding the semester. So here, uh, so this is how this complete code is broken. So it means that this complete code I can break into multiple units. So but that's why this will be called as a non-atomic. And if I consider the telephone number or subject name just like database engineering, then in that case we cannot divide database engineering as database and engineering or some another. Okay, that's why here this title of the course I can say that this is a atomic in nature. A relational schema R is in first normal form if domains of all attributes of R are atomic. Okay, if consider this example R is my relation and there are three attributes A, B and C, and A, B, C three are having atomic domains, then I can say that R is in the first normal form. If A is atomic, B is non-atomic and C is also atomic, in that case as B is non-atomic, R will not be in the first normal form, R will be in the denormalized form. Okay, so a relational schema R is in first normal form if domains of all attributes of R are atomic. Non-atomic values complicate the storage and encourage redundant repeated storage of the data, and that's why set of account stored in each customer and set of owner stored in each account, we assume all relations are in a first normal form. Okay, so whenever we are dealing with this, whatever the schema up to now we have studied, all these are following the standard rules. Just like department name, I cannot divide further. Course ID also. So while giving the course ID, even though this course ID is having its own uh, the identification, but still we have considered this as a non-divisible unit. Okay, so this is regarding the first normal form. Any doubt in this? Any doubt in the first normal form? Can anyone give me the example of non-atomic domains other than whatever we have discussed orally or by written? So okay, let us see for few of the details. Atomicity is actually a property of how the elements of domain are used. Example, strings would normally be considered indivisible, that if we enclose these into single or double inverted comma, these become a string and we cannot divide further. Suppose that students are given the roll numbers which are strings of the form CS0012, EE112327. These can be also considered as a uh, non-divisible. If the first two characters are extracted to find the department, the domain of rule number is not atomic. Okay, if we explicitly know that CS get automatically, then we can say that this is also non-atomic. If while entering we do not make any differentiation between these two, then we can say that this is a atomic. So but this will be a bad idea, leads to encoding of information in application programs rather than in database. So what is desired? So goal is to devise a theory for the following. So decide whether a particular relation R is in good form, that it doesn't repeat a information. In the case that relation R is not in good form, decompose it into set of relations R1, R2, or it may reach up to Rn, such that each relation is in good form. The decomposition is a lossless joint decomposition. So here we are using two concepts, functional dependencies and multi-value dependencies. So okay, so this point, that is first normal form, we repeat into next lecture also. So please, if you are having doubt regarding the atomic domain etc., you can ask me. Yes, atomic domain employee ID is a correct example, because employee ID we don't divide this into number of this number of subparts.